from University of Michigan, and he's going to talk about an explicit supercuspidal local Langlands correspondence. Yes, welcome.
All right, well, thank you very much to the organizers for their kind invitation. It's very nice to be back, at least in spirit. And I'm going to try to imagine what it would feel like to go and get a bent spoon ice cream at the end of my talk. What I want to discuss today is a project that's been ongoing for a couple of years for me. And at a very early stage of this project, oh, there is a chat here. I'll try to pay attention to chats. Oh, that's just a general, okay. I spoke about this at a fairly early stage at a conference at the IS about 2 years ago. And I had been working for a few months on it, and I felt reasonably confident. I understood where things are going, and I was eager to share my ideas. And in hindsight, this may have been a little premature because, as it turned out, there were a number of details that kept me busy for those remaining a year and a half or 2 years. But now I can finally confidently give this talk and explain all the details, at least as far as the time allows it to me, but I'm happy to discuss also further with anybody who is interested. So here is my setup. I have let me try and make this just a little bigger. There we go. So I have a periodic field F, which means that it's a finite extension either of QP or of FP double parenthesis T. And I fixed the separable closure. So I have the absolute Galois group. And I have the closely related Weil group. And I'm going to look at what Arthur calls the local Langlands group, which is a simple variation on the Weil-Deligne group, which is just the product of the Weil group and the algebraic group SO2C. And then we consider a connected reductive group G defined over F. So we have our favorite examples, maybe the group SO2 or the group GLN, or maybe the group SP4, or if you have some Russian heritage, maybe you'd like to think of the exceptional group E8. And then we consider the complex dual group associated to this by duality of root data. So for example, we'll be having PGO2, or again GLN, or SO5, or again E8. And this complex dual group comes equipped with an action of the Galois group. And so we can form the semi-direct product, which is the L group. We can use either the Galois group or the Weil group for this construction, and both are useful. And what I want to discuss today is a construction or a description of the local Langlands correspondence for this group and for supercuspidal parameters. I'll say in a second what I mean by this. So let me first remind you of what the local Langlands correspondence is, or what I understand by this name. So it's going to be a collection of a few conjectural statements. The first conjectural statement would be that if you start with the Langlands parameter, which is a homomorphism from the local Langlands group into the L group of G, subject to certain technical conditions, there should be an associated L packet on GF, which will be a finite set of irreducible admissible representations of this topological group GF. And certain properties of the parameter are going to be reflected in properties of the L packet. For example, there is a property of the parameter to be tempered, which means that the image of the Weil group in the dual group is bounded. And that property is supposed to be reflected to a property of the packet being tempered, which means that every member of that packet is tempered, which means in terms of matrix coefficients, that those matrix coefficients are going to be almost square integrable modulo the center. So in L2 plus epsilon for any epsilon. There is a notion of the parameter being discrete. That means it doesn't take image in any proper Levy subgroup. And that's supposed to be reflected in the corresponding property of the packet being essentially discrete. And essentially discrete is going to mean that the matrix coefficients now are indeed square integrable modulo the center. And then there is a property of the parameter being supercuspidal. And these are the parameters that I'm going to discuss in this talk. So let me mention what this means for me. This means that the parameter is discrete. And if you restrict it to the SO2 part of the local Langlands group, it is trivial. So it's really a discrete parameter starting from the Weil group rather than the local Langlands group or the Weil-Deligne group. And that is supposed to correspond to a supercuspidal packet, which again for me means every member of the packet is a supercuspidal representation. And so its matrix coefficients are actually compactly supported modulo center. So that's the first part. But then we would like to also understand, not just have a map between parameters and packets, we would like to understand the members of each individual L packet. So let's call this internal structure. So for the internal structure, what we're going to do is we're going to consider the centralizer of the image of this parameter in G hat. The image of the parameter is in LG, and G hat acts, of course, on LG by conjugation. And we're going to take the elements in G hat that centralize the entire image of the parameter. So first, let's consider the simpler case where G is quasi-split, which means it contains a Borel subgroup defined over the ground field. And in that case, the picture is fairly simple. The members of the L packet are supposed to be in one-to-one correspondence with the irreducible representations of a certain finite group. Which finite group is it? You take the centralizer S phi and you divide out the center of the L group from it. And then you take the group of connected components. That gives you a finite group. Its set of irreducible representations is supposed to be in one-to-one correspondence with the packet. There is a particular irreducible representation, the trivial one, and that's supposed to correspond to a generic representation in the packet. And in fact, there's supposed to be a unique generic representation, a unique representation that has a Whittaker model once you fix a Whittaker datum. And this is what is called sometimes Shahidi's conjecture. It was made in a paper from the 1990s. Now, when G is general, no longer assumed quasi-split, then the structure theory of reductive group tells you that it comes about as a pair. There is a quasi-split group, and then there is also a class in the first Galois cohomology of the adjoint quotient of this quasi-split group. And so, I want to actually avoid some technical discussions. And so I'm going to replace this first Galois cohomology of the adjoint group with the first Galois cohomology of the actual group GQ itself. And if, of course, this class may or may not lift, let's assume for simplicity that it does. And then a result of Kottwitz that reinterprets Kneser's work on Galois cohomology gives an interpretation of this set in terms of the L group. So you take the center of the L group and you take its group of components. That's a finite abelian group. You take the Pontryagin dual. There is a canonical bijection like this. This is a result of Kottwitz. And so now what we can say is that we expect the L packet to be in bijection with the set of irreducible representations. We take again the component group of the centralizer, but we, instead of dividing by the center of the L group, we specify that the center of the L group is going to act by the character that is given by this Galois cohomology class. And so this bijection is what I'd like to refer to as the refined local Langlands correspondence, because now we can access an individual representation rather than an L packet of representation. And it's parameterized by a pair, a Langlands parameter, and then an irreducible representation rho of the centralizer or component group of the centralizer. And this pair is what people sometimes refer to as an enhanced Langlands parameter. And I'll just make a verbal remark that if you want to not simplify the situation and assume that the class lifts to the first Galois cohomology of the group G, and work with the Galois cohomology of G add, then you need to go into alternatives to Galois cohomology and talk about Galois adverbs and things like that. But at the end of the day, as far as the centralizer group is concerned, there is a simple modification that does the job. What you need to do is map the centralizer to the adjoint group of the dual group and then pull it back to a simply connected cover. But then all the work is involved in saying what you mean by this psi here. Anyway, the only reason I say this is because I want to give you an example a few minutes later that involves this modified centralizer group. And the third part of the conjecture concerns endoscopy. So for this, we're going to assume that phi is tempered. And more generally, if one doesn't want to assume phi is tempered, one needs to work with Arthur parameters rather than Langlands parameters. And then we're going to take a semi-simple element in the centralizer group. And that pair of parameter and semi-simple element in the centralizer leads to a smaller reductive or a reductive group that's usually smaller than G. And the way you say what it is the following. You first say what is the dual group. That is going to be the connected centralizer of this semi-simple element. And then you say what is going to be the L group, which is roughly the dual group times the image of the parameter. This is related in a certain way to the L group that I want. That is somewhat technical to discuss, so let me not go into this discussion. But in any event, this data specifies a quasi-split connected reductive group H. And by the way things are set up, the parameter I'm starting with, which took values in the L group of G, now takes values in this basically L group of H. And so we have an L packet for G and an L packet for H, and we can form a virtual character for both G and H from these L packets. The way we do this is the following. We're going to sum over all the rows, which up here by this bijection enumerate the packet. And we're going to take the, say, Harishchandra character of each corresponding member of the packet, but we're going to put as a weight in front something that's made out of the row, namely the trace of this finite dimensional representation row at the element S. And we can do the exact same thing on the side of H. Let me use primes to denote what's happening on the side of H. So the factor parameter will be phi prime, the rows will be rho prime. And then I could basically write exactly the same, the trace of rho prime S. Now S is central, and so this trace of rho prime S, what this ends up being is basically the dimension of rho prime. And the conjecture is that those two characters agree. In what sense do they agree? If you feed a test function into the character for G, that's supposed to give you the same as if you feed a corresponding test function for H, where F and FH are related by so-called endoscopic transfer, which is a celebrated theorem of endoscopy. Every time you have a test function for F, there is a test for G, there is a test function for H with matching orbital integrals. And so these are these matching functions. So this is, those three statements are for me what I call a refined local Langlands correspondence. And so now I can state the result that I want to discuss today. So the result is the following. I need to make two assumptions under which the result holds. The first assumption is that G, the reductive group that I work, splits over a tame extension of the base field. Most groups will do this, but not all. There are some groups that certainly do not do that. And the second assumption that I'm going to make is that P, the residual characteristic of the ground field, does not divide the order of the Weil group. The second assumption can be relaxed a little bit, but then the result also becomes weaker. So let me keep this assumption for the talk. And then under these assumptions, the results are the following. I'm going to number them in the same way that I numbered the conjectures. First of all, there is an explicit construction that matches a phi, a supercuspidal parameter, to an L packet pi phi for any supercuspidal phi. So what I want to emphasize are two things. The first thing is that there are no assumptions on the supercuspidal parameter. Any discrete parameter with trivial monodromy is covered by this construction. And the second is that this construction is completely explicit, which means that if in an application you have a parameter that you have explicitly described, then you can describe each member of the packet explicitly. You can say, for example, how do you get this representation via compact induction? What is the compact open subgroup from which you're inducing? What is the finite dimensional representation on it that you're inducing? The second part concerns the internal structure. So the internal structure of L packets holds, which means that we have a bijection as described up here between the packet and the corresponding part of the centralizer. Now, I want to say a little bit more about this. This internal structure is supposed to be canonical. Once you fix a Whittaker model, this bijection has to be fully pinned down. What I can show is that this is canonical when phi is regular, which is an adjective I'm going to explain in a moment. And it involves some auxiliary choices, in fact, one auxiliary choice in general. And so I'm currently working towards removing this auxiliary choice. It shouldn't be there, and I can tell you later exactly where it occurs. But even with the auxiliary choice, there is a bijection between the two sets, and it has the properties that it needs to have. And moreover, we have results towards Shahidi's conjecture. So Shahidi's conjecture, the existence and uniqueness of a generic constituent within each of those L packets holds when phi is of depth 0 or toral, again, adjectives that I'm going to explain. In fact, I think we have Shahidi's conjecture in general, but those are the cases that have been written up. And in a work in progress with collaborators, we have come up with an argument for the general case, but that still needs to be written up and verified. And then the third result concerns endoscopy. So stability, which is a special case of endoscopy, stability holds for phi of depth 0 or toral, and endoscopy holds for phi toral. For this, I actually need to assume that P is sufficiently large because this uses the existence of an exponential map, and that exponential map has to converge on a large enough domain so that we can make our statements. So this P large is often larger than P does not divide the order of the Weyl group. So these are the results as they stand at the moment. Let me tell you a little bit about work in progress that is still ongoing. So the first project that I want to mention is when phi is of depth 0. What remains to be done is endoscopy and the canonicity of the internal structure. So this is work in progress with Steven de Backer and Cheng Tsai. And then when phi is positive depth, again, these are adjectives that I'm going to explain in a moment. There is work on endoscopy and the genericity that I just mentioned. So this is work in progress with Jessica Finson and Lawrence Spice. And then there is work in progress on the formal degree conjecture due to Hiraga, Ichino, and Ikeda. And this is the thesis work of a student of mine, David Schwein, which is essentially complete now for regular supercuspidal parameters. So now that I have, so this is the result both in what is in progress and what is already complete. And let me give you a cartoonish mental picture of how you may want to think about the landscape of supercuspidal parameters.
Can I ask a question? Yeah.
Yes, please.
You're mentioning Jessica or maybe Julie Kim. Do you actually use her classification of the supercuspidals? You need something explicit at some point?
No, I do not use Jessica's result, which would state that all supercuspidals come from JKU's construction if P does not divide the order of the Weil group. Her result is in some sense in line and compatible with what I do, but I do not use it. I do, however, use construction.
Okay.
Can you remind what stability means?
Stability means that when you consider this formal linear combination here, but you put S equals to 1, which actually ends up being this combination. When you put S equals to 1, you get a dimension of rho. Then you want this virtual character to be not just invariant under conjugation, but also invariant under conjugation by the algebraic closure, points of the algebraic closure. So these are not real conjugacy classes because, of course, the point in the algebraic closure don't act, but it's still an equivalence relation. You can ask whether two regular semi-simple elements happen to be conjugate if you base change to the algebraic closure, or in fact, in this case, because I'm using also positive characteristic separable closure. And this turns out to be an equivalence relation that's looser than conjugacy. And stability means that your virtual character is invariant under this equivalence relation. All right, so here is my little cartoonish picture of the landscape of supercuspidal parameters. So here is the landscape, and pretty much everything in it is regular. So what does regular mean? Well, there is a technical definition and a less technical definition. I'll give you the less technical definition, which is stricter. So everything.
Sorry, Tasho, could I just ask a couple of questions?
Yes, please.
So is part of the statement is that these packets cover all supercuspidals?
No, this is, thank you for this question. No, this is not the case. These packets cover what I would call semi-simple supercuspidal representations. And the way you can define this is you can look at use construction, which I'm going to mention at some point. And there is a depth zero piece, which you can think of the depth zero socle. And that thing is supposed to be semi-simple. That is, if you look, it's related to a representation over the finite field, and there is a Jordan decomposition due to Lustig. So there is a unipotent part and a semi-simple part, and you don't want to have any unipotent part. Yes, but let me finish answering this question. Conjecturally, all the supercuspidal representations that do not fit in these packets will live in packets where they're also non-supercuspidal discrete series representations. And they're going to correspond to discrete parameters that do have SO2 monodromy.
I see. And one other question is that, you know, your the conditions you wrote down don't nail down what the Langlands correspondence is.
They don't, no.
So how do you, so to speak, know it's the right one?
I'll tell you towards the end. I have a sufficient knowledge of the Harishchandra characters for the representations, and this does not give a formal proof, but it strongly suggests that this is the right one. I do not have a formal proof that it is the right one. I do not have a uniqueness characterization. I'm not aware of a list of properties that characterizes this uniquely. This is one of the things I'm thinking about, but I don't have any formal statement to make.
But your work maybe suggests such a thing in terms of the character?
It may suggest it, but I don't have a statement that I'm ready to make about it.
Okay, thank you.
But I'll mention to you in the end what I mean. So regular, here is a definition. Consider the centralizer of the image of inertia, not the image of the full Weil group, the image of inertia in G hat, and ask that this be abelian. I have a definition of regular that's slightly weaker than this, but this is easier to write down. And one of the things that this implies is that the entire SV is also abelian. So if I scroll up and remind you of the internal structure, you're going to see that in the regular case, you're dealing with irreducible representations of an abelian group. So they're all just characters. And so the internal structure becomes much simpler in the regular case. when and so then there's some things on the outskirts here that fail to be regular. And in that case, SV is often non-abelian. And this makes the internal structure much more challenging because you'd have representations, irreducible representations of higher dimension, and that's going to match certain multiplicities on the side of G and so forth. And then you have, every once in a while in here, very special points, which are these toroidal points. So what do they mean? We consider the centralizer of, you can consider the upper numbering filtration of inertia. Just go down far enough until you see the kernel of this parameter. And just the next level up, take that and take the centralizer. And you want that to be very regular. So you want this to actually be a torus. So these are very kind of special parameters. So now let me give you a little bit of an illustration of the difference between regular and non-regular and how things happen. So for SL2, all supercuspidal parameters are regular except for a single one exception. And so what happens is every regular supercuspidal L packet has 2 points for SO2. Here are different L packets in my cartoon. And if you look at the inner form, that's the norm 1 in the quaternion algebra. Also, every regular supercuspidal L packet has 2 points there. And this group, this modified centralizer, whose representations are going to control both the L packet for the group and its inner form, that's an abelian group Z mod 4Z. So it has 4 characters, 2 of them parameterize the packet for SO2, 2 of them parameterize the packet for D1. And the unique non-regular supercuspidal L packet, there, the 2 points for the compact inner form fuse together to a single point, whereas each of the 2 points for SO2 splits up into 2 points. And so you have a packet of order 4 for SO2 and a packet of order 1 for the inner form. And there, this modified centralizer group becomes the non-abelian group Q, which is the quaternion group. And this quaternion group has 4 irreducible representations of dimension 1 that match with these 4 red dots in the L packet for SO2, and 1 irreducible representation of dimension 2, which matches with the single element in the L packet for the inner form. All right, so this is roughly the picture. And now the next thing I would do is I would start explaining how the construction works, first in the depth 0 case and then in the positive depth case. Are there any questions before I go into that?
So when you say the toroidal ones are these very rare special points, like what do you mean by that? Because I think of the toroidal ones as being like very generic.
No, so no, the toroidal ones are not really generic. They're quite special. It's because, it's a rare event that you go to find the kernel of your parameter, and then the next level up, the image is already regular in the group. That's a rare occurrence. Usually,
well, if I take like a random parameter of depth R, something like that, then it'll probably, the level R thing will probably be regular because it'll probably be, the image will be as big as possible. So the centralizer will probably be very small. Like if P is large.
Okay, maybe, yeah, maybe that's a fair assessment too.
Yeah, I mean, it's obviously not super important. I just wanted to hear if you have some.
No, to me, these are very special, but I've not actually made kind of a probabilistic assessment as to how special they actually are, because to me it seems like if you pick a generic point, you're going to find it. But anyway, maybe I don't have the right mental picture.
Well, maybe there's different ways you can think about counting them. Like I think if you count them by depth, then what I'm saying is true. But maybe there's other ways of counting them where it's the opposite, and they're the regular ones are the most common. I think it might be an interesting thing to think about.
Yeah. So thank you for mentioning this. Maybe I should spend more time meditating on that. Okay, so let me explain how the construction works. It splits into two parts, the depth zero part and the positive depth part. So here is how the depth zero part would work. So depth zero, this means that the parameter is trivial on wild inertia. Okay, so then this, I'm going to take this parameter, and it turns out that it factors canonically through the L group of a maximal torus. And this maximal torus is maximally unramified and elliptic, which means compact modulo center. And so, moreover, this factored parameter gives us a character for this torus via the local Langlands correspondence for tori. So what we obtain is a pair, S theta. S is a maximally unramified elliptic maximal torus. Maybe I'll copy this down here. And theta is a character of this torus, which is of depth zero and non-singular. And this non-singular is a p-adic analog of the non-singular property that is defined by Deligne and Lustig for finite groups of Lie type. Basically, what it says is that this character doesn't kill any co-root when you interpret what this means properly. And so then, because this torus is elliptic, it leads to a point in the Bruhatitz building of G. And so this point endows G with an integral model. And we can take the special fiber of this integral model and take its reductive quotient. And then we find ourselves in the setting of finite groups of Lie type, with one very important subtlety that usually this reductive group over the finite field is disconnected. And so we have to work with this. Let me first explain to you the results due to Lustig in the connected case, and then I'll say what needs to be generalized and what changes when you move to the disconnected case. So consider first, I'm going to reuse the symbol G, G to be a connected reductive group over a finite field, K. This torus here would give us an elliptic maximal torus in G. And this character is going to factor through a character. I'm going to switch to QL-bar coefficients. That is non-singular. And then it's a result due to Lustig, which, well, it's partly due to Deligne-Lustig and partly due to Lustig, which says the following thing. If you form the Deligne-Lustig induction for this pair of torus and a character, this is usually a virtual character of the group, but it turns out that up to a well-understood sign, in this particular case where theta is non-singular, this is actually a real representation, and it's a cuspidal representation of this finite group of Lie type GK. So this is what was proved by Deligne and Lustig. What later was proved by Lustig is what is the structure of the irreducible components of this cuspidal representation. So Lustig proved that this is of multiplicity 1. So each irreducible constituent occurs exactly once in it. And moreover, if we look at the set of irreducible constituents, so let me use square brackets to denote this set, this turns out to canonically be a torsor under a certain finite abelian group. Which finite abelian group? You take the Weil group of this torus, you take its rational points, you take the part of it that fixes the character theta. By now, you can prove that this is an abelian group. Of course, it is finite. And you take its Pontryagin dual, and there is a canonical, simply transitive action of this finite abelian group on the set of irreducible constituents of this representation. So this is Lustig's result. And now, we need to move to the case of G is disconnected, because this is typically what we're dealing with when we're coming from a p-adic group. So now G disconnected. I don't want to be super precise about what class of disconnected groups I take. There are certain restrictions on it by virtue of them coming as reductive special fibers of parahoric groups. But the point is this: for this class of groups, at least, one can check the following thing. So again, the first thing is that you can run the Deligne-Lustig theory in the disconnected setting perfectly fine. And it's, I'll write down the Deligne-Lustig variety in a moment. There is no difficulty with that. And again, you prove that up to this sign that you know, this is a cuspidal actual representation of this finite group of Lie type. I don't know if it's legal to call it a finite group of Lie type when G is disconnected, but let's still do this. However, what fails, the problem that you have, is that this is no longer multiplicity 1. And so we now need to understand the structure of this, and we need to understand it together with multiplicity. And so in particular, we wouldn't expect to understand it by a torser construction. It's a more complicated situation. And so the solution to this problem is to take inspiration from the classical theory of parabolic induction and how you decompose parabolic induction, and you do this using intertwining operators. So we're going to decompose using intertwining operators. But of course, we need to explain what intertwining operators are. So let me try to do this very briefly. So first of all, we consider the Deligne-Lustig variety in whose cohomology this cuspidal representation is going to be realized. The formula for this is exactly the same as in the connected case. You pick a Borel subgroup containing your torus in the connected piece, and you divide the disconnected group G by the unipotent radical of this Borel subgroup, and you write down the formula that you would write in the connected case as well. And so in the compactly supported cohomology of these varieties where you find the representation. So now we're going to construct an intertwining operator by means of a correspondence construction on this variety. So the first thing is very simple. So we're going to have an intertwining operator for every element in the normalizer of this torus that fixes the character. And the first part is very easy. We're just going to push by this element. So we're going to use right multiplication, and that's going to beam us from the variety for this Borel to the variety for the conjugated Borel. This is very much like in the classical case where you would precompose a function which is a section of your induced representation by the Weil group. And so you'd push it and you'd change the Borel. But now you have to return the Borel back to where it came from. In the classical setting, this is a standard intertwining operator given by integration along parts of the unipotent radical. But in this geometric situation, this comes from recent work of Bonafé, Dat, and Rouquier, which give a construction in the geometric setting very much like the standard intertwining operator. So here is what they do. They define a variety by a similar formula. I can write it down at the end of the talk if anybody is interested, but it's based on two Borel subgroups. And they define a closed subvariety of that. So we have a closed immersion here, and this closed subvariety surjects, oh, my surjection is too long. Let's take a shorter surjection. Surjects onto the usual Deligne-Lustig variety, and this is an affine space bundle. And on the level of the linking variety, what you can do is you can switch the two Borels and put a Frobenius on one of them. And then you have a similar construction. There is a closed subvariety here, and then an affine space bundle going down to here. And the main result of, at least of this section of their paper, is that this becomes an isomorphism on the level of cohomology. And so when we take this isomorphism and we compose it with what we got in A, we end up with the intertwining operator. Let me call this Rn, acting on this Deligne-Lustig induction. So this is going to be our geometric version of the intertwining operator. And the problem that we're facing is a familiar problem from the classical theory, that these intertwining operators end up not composing quite right. If you compose two of them, you don't get the intertwining operator for the product of the two normalizing elements. You almost get it, but you're off by a scalar, just like in the classical case. And so the problem becomes the same. Can you find a renormalization of these intertwining operators so that they do compose properly? And in the classical setting over local fields, there is a conjecture due to Langlands that tells you exactly how to renormalize the intertwining operators. You have to multiply them by a certain prescribed collection of ln epsilon factors, and then they're supposed to multiply properly. And Arthur was able to prove this for real groups using the already established local Langlands correspondence. And what he was able to do for p-adic groups was a weaker result, where he couldn't prove that Langlands' recipe is the correct one, but he was able to prove at least the existence of a normalized collection of intertwining operators. And I have a similar result here as well. What I can do is I can show that a normalization exists. And the way I do this is I just study the obstruction to the existence of a normalization and show that eventually it has to vanish for abstract, not too abstract. I mean, there is a devisage argument which boils down to an explicit calculation in type D to N, but at the end of the day, it doesn't tell you what a normalization, it doesn't give you a good normalization, it just tells you that one exists and you can choose it. But as an application of this, we obtain the following description of the internal structure of this reducible Deligne-Lustig representation. It is given as a direct sum parameterized by the irreducible representations of the normalizer of the torus, the part of it that fixes the character, and only those whose restriction to the torus equals a multiple of that character. And then you have a piece corresponding to this representation, and this piece comes along with this row. And so in particular, this parameterizes the pieces of this Deligne-Lustig induction by exactly those rows, and it matches multiplicity. That is, the multiplicity of an irreducible piece in here equals obviously the dimension of this row, which is the same as the multiplicity of theta in that row. So you get a parameterization matching multiplicities. And this is, if you like to think of analogy with the classical case, this is the analogy of the Harish-Chandra basis theorem in this setting. And now if you combine this with Moy-Prasad theory, which tells you how to pass between depth zero supercuspidal representations and cuspidal representations over the finite field, and a miracle, you end up with the internal structure of depth zero L packets. Now, what do I mean by a miracle? Well, if you just take Moy-Prasad theory, you would get an internal structure of depth zero L packets in terms of such sets here, but which involve the normalizer of your torus in the group. But you really want to parameterize them in terms of dual data on the dual side. And connecting this to the dual side is something quite miraculous that I still don't understand why it works. It just does. And it does canonically, which is even crazier. However, there is one non-canonical thing here, and this is what makes my result about the internal structure non-canonical. It has one auxiliary choice. What is it? Well, it's the choice of a normalization of intertwining operators. If I can choose that canonically, then the internal structure will be made canonical. And so in my ongoing work, I've reduced this choice to unramified groups of type A. And so I'm confident that in that particular case, I can see what's going on, and everything else bootstraps from there. But even in that case, I still don't know exactly. So that's still ongoing.
You mentioned Arthur in the classical group case has a normalization. He verifies this, no?
No, I was just drawing an analogy to the classical case where you want to decompose parabolic induction rather than Deligne-Lustig induction. And there you still have to normalize the intertwining operators there. And Arthur has a result there that a normalization exists. But
so it doesn't apply here.
No, those are just two different words that are in some philosophical analogy, but they're not in mathematical relationship.
I misunderstood.
because it's a funny business. I mean, there you're trying to parameterize precisely representations that are not discrete series. They're tempered but not discrete. Here you're trying to parameterize supercuspidal things. And I find it very, very strange that you end up using similar ideas at the opposite end of the spectrum, where you're dealing with supercuspidal representations. So obviously you're not decomposing parabolic induction, but still ideas are somewhat similar. All right, let me just introduce one notation here for the representation of the p-adic group that you get from the representation of the finite group by compact induction. So these are going to be the representations which via Moy-Prasad theory are going to populate the L packet. So this is the depth zero situation. Now I want to move to the positive depth situation.
Can I ask, this analogy is kind of surprising, analogy between parabolic induction for p-adic groups and connected Deline's, I mean.
So the spirit of this analogy was certainly mentioned already in the paper of Deline and Lustig, that they think of their induction as a generalization of parabolic induction, which you can do because if you apply Deline-Lustig induction to a split torus, or more generally the most split torus that is a levy, then Deline-Lustig induction recovers parabolic induction.
But that's with a finite field, right? Not for p-adic groups.
That's right, but I mean, this is happening, everything here is happening over the finite field. Up to this point, only when you involve Moy-Prasad theory, you get to the p-adic group.
But you're suggesting that it's analogous to parabolic induction for p-adic groups, are you?
No, I'm not suggesting this. I'm suggesting that this analogy, which they discuss, can be moved further to decomposing the induced representations. Just like you can decompose a parabolically induced representation using intertwining operators, you can decompose a Deline-Lustig induced representation using the geometric version of intertwining operators. That's what I was trying to say. All over the finite field.
Okay.
And this is most interesting in the disconnected case, because in the connected case, you have Lustig's result of multiplicity 1, which is reflected here by the fact that this character theta extends non-canonically to this abelian group. And so this set of irreducible representations becomes the set of extensions of this character to this group. And this is, of course, a torsor under the characters of this Weil group. And so things match up. All right, so the positive depth case is, of course, the case where the image of wild inertia is not trivial. And so that just begs you to take that image and do something with it. And so what we're going to do is we're going to take the centralizer of this image in G hat. This is going to be a Levy subgroup of G hat, and it's going to be normalized by the entire Weil group acting through the image of the parameter. That's going to give it a Galois structure. And what you end up on the non-dual side is a twisted Levy subgroup of G. What is a twisted Levy subgroup? It's a reductive group defined, a reductive subgroup defined over the base field, which over some extension becomes a Levy subgroup. So for example, any maximal torus is a twisted Levy subgroup, but only the split maximal torus, or the maximal torus that contains the most split torus, is a Levy subgroup. And a compact maximal torus will never be a Levy subgroup, but it's a twisted Levy subgroup. And another example is in the unitary group UN, you have twisted Levy subgroups of the form UP cross UQ. So these are just some examples. And what we have is, again, we're going to work with a factorization of our parameter now through this twisted Levy subgroup. And the way things are set up, this factor parameter is going to be essentially of depth 0. What do I mean? Remember, depth 0 parameter is one that kills wild inertia. Essentially, depth 0 parameter means it sends wild inertia into the center of the dual group. And of course, M was made so that wild inertia goes into its center. And, but a very simple character twist of the depth 0 story that we were discussing so far covers essentially depth 0 parameters. So by that, we have an essentially depth 0 L packet already waiting for us on M And now the question becomes, can we bootstrap this L packet to G? So the goal here is to realize the functoriality that is inherent in the embedding of LM into LG. So the first observation, or maybe proposition, is we know that the centralizer of the parameter in M equals, canonically, the centralizer of the parameter in G. This is not difficult to show. So because we are aware of internal structure, what we then expect is to have a canonical bijection between the L packet on M and the L packet on G that is going to reflect this functoriality. Now, when I say L packet on M and L packet on G, I have to specify a little bit what I mean, because if you remember the internal structure, we're not taking irreducible representations of this entire group, but only a subset of them given by a certain central character. But now, if you put all central characters together so that you're working with the whole group, that has the effect of putting all inner forms together. And if you do this, you get the so-called compound L packet, and that's what I mean here. So this is the L packet for M and all its inner forms. This is the L packet for G and all its inner forms. And you expect a bijection from the one to the other that's canonical. So let's try and construct it. So this would be the construction of the transfer. And again, I'm going to use this term functorial transfer somewhat loosely. I do not have a definition of what functorial transfer means in the local setting. I don't think we currently understand this, but I'm going to give some intuition with using character formulas of what this might mean. So here is what you do. You start with this essentially depth zero supercuspidal representation that is a member of your essentially depth zero L packet. And it's essentially depth zero. What does that mean? Well, it's a character twist of a depth zero representation. Here is the character delta, and this left superscript 0 is supposed to mean an actual depth zero representation. Of course, this decomposition is not canonical, but it's not going to matter. And then you take this character delta, which is a character of the whole group M, and there is a generalization of a lemma due to Howe, we'll call it the Howe factorization. So Howe factorization allows you to take a character of a maximal torus of GLN that has a certain admissibility property and break it up into a product of characters that are generic, which is a very strong property. And you can do the same with a general reductive group and with a character of a twisted Levy. So this is what we're going to do. And with this, delta is going to unfold and give you an entire tower of twisted Levy subgroups that interpolates between the twisted Levy M and the entire group G. And also it's going to give an entire sequence of characters, which are each lives on the corresponding twisted Levy subgroup and is generic. And this is precisely the input that you feed use construction to produce a supercuspidal representation of positive depth for G. So using this input, so the tower of twisted Levies, the sequence of characters, and this depth zero representation, JK use construction produces a positive depth representation. So positive depth supercuspidal irreducible representation of G of F. And so the question we want to ask ourselves now is, well, first of all, there is a theorem that one needs to prove, is that this result of this construction depends only on the essentially depth zero representation of M and not on, you know, the choice of factorization here, the choice of Howe factorization. There is various ambiguities in these, but it turns out that none of these ambiguities affects the result. And this uses work of Hakim and Murnahan, who have studied what ambiguities affect use constructions and construction and what do not. And so now comes the question, is this map that you now have a well-defined map, is this map the functorial transfer that you want? And in order to answer this, we turn to Harish-Chandra characters. So these were studied in the setting of use construction by Jeff Adler and Lawrence Spice and Stephen DeBacker. And basic endoscopic considerations tell you that you expect to see the following formula. So I'm going to write down a formula that you expect to see. And I'm going to put all rows together back so that we have this reducible cuspidal representation, which we compactly induce. We're not going to worry about the fact that it's reducible. And when you feed in a shallow element of the torus SF, shallow in terms of the Moy-Prasad filtration, this is what we expect to see from the endoscopic point of view. There is a well-defined sign called the Cotwit sign. And then there is a root number of a certain virtual Galois representation made up of the character module of the torus S and the character module of a reference torus, which is the minimal levy in the quasi-split form. And then we have a sum over the Weil group. There is an endoscopic quantity, and then there is the character theta. Now, I don't want to go into details about these pieces. I can discuss it after the talk with whoever is interested. Now, what do we actually get is interesting from the construction that we just performed. Well, we get something that's similar, but not quite what we want. And that's very disconcerting. So what we get, it starts off promising. It starts off with this Cotwit sign. We get the correct root number. And then we get the correct sum, but then things start to fall apart. First of all, we get not quite this endoscopic quantity, but the character twist of it, which I'm just going to denote by a tilde. And then we get an auxiliary sign character. And then we get another auxiliary sign character until we finally get what we want. Oops. And so when I got to this point, I became very upset because everything seemed to be going perfectly. All the constructions were beautiful and canonical. And at the end, you look at something and you realize this is not what it's supposed to be. How could it be that this is not what it's supposed to be? And after a lot of studying, it turns out that the source is actually a mistake in JKU's paper. And Jessica Finson discussed that mistake in her talk a couple of weeks ago already. I'll just remind you what had happened there is that JKU uses the Weil representation, and he quotes a paper of Girardin from the 70s. And in Girardin's paper, there is a lemma, and this lemma states a formula for the character of the Weil representation, and that formula is wrong. If you look at the proof of the lemma, the proof is correct, but the formula it derives does not match the formula in the statement of the lemma. There is a discrepancy between the two by a sign character, possibly due to a clerical error of just typing or whatever it was. But the formula used in Yu's paper is the incorrect formula from the statement of the lemma. And that has disastrous consequences. It breaks down certain intertwining results that Yu has in his paper that are crucial for his proof that his construction produces irreducible supercuspidal representations. And so Jessica Finson proved that the construction still produces irreducible supercuspidal representation despite the faulty proof by just substituting it with a different proof. However, the fact that the intertwining results fail is a kind of indication that something is not quite right. And in particular, the intertwining results are crucially used in the computation of Harish-Chandra characters. Now, these formulas still work because they are at shallow elements, and there you can get by without this. But as Lawrence Spice was trying to generalize his formula beyond shallow elements and beyond certain compactness assumptions that he had made, he discovered this error. And he linked it to this character here. But he only did his analysis for tori S, which were unramified. And it turns out if you consider more general tori, you also link it to this and also to the character twist here. And so in joint work with Jessica Finson and Lauren Spice, what we do is we give a modification of use construction. And this modification has the following, well, how do we modify use construction? We construct a certain natural sign character in a very general setup and twist use construction by it. We don't need the full U datum. We only need a reductive group, a twisted Levy subgroup, and a real number for which the center of the twisted Levy has a generic element of that depth. So just from this data, you can write down very natural, but it took us over a year to get it right, sign character of the parahoric for the twisted Levy. And when you twist use construction by it, what you get is, first of all, you restore the validity of the intertwining results, and in particular of Yu's original proof of his construction producing irreducible supercuspidal representation. And secondly, these erroneous or extraneous auxiliary character in double star go away, and the formula that you want lines up perfectly with the formula that you get, and that completes the construction in the positive depth case. So maybe I'll stop here, but to Akshay's point raised earlier, this formula for the Harishchandra character ends up pinning the representation among all possible choices uniquely. And so that's why I write this formula. You can ask me, well, why do you want this formula? And that's where things become more philosophical and less mathematical. I do not have a list of properties which imply this formula and have to be satisfied. I know that if I write this formula, endoscopy is going to hold, provided that I have the correct generalization to non-shallow elements, which Lauren is currently working on. But once you are at the stage that you think that this is the right formula that you want, this formula pins down the representation uniquely. So that's my reason to believe that this is the right thing to do. So I'll stop here.
So questions?
Can I ask you a question?
Yes, please.
Yeah. So we mentioned like there was some problem with some lemma in the underlying paper, or the
yes.
formula. So would that formula still be true if you use the other sign? So what I mean is like if you talk about the representation of, let's say, of GNNQ or GUNQ, right? Of FQ, right? So you have two choices. When you Q is out, then you have two choices yeah. I mean, like you can twist it with the quadratic character of the determinant, right?
Mm-hmm.
So would the lemma still be true if you use the other one?
No, it is not as simple as just taking the quadratic character of the determinant. The character that we end up using is vastly more complicated. It has three pieces. It does use the quadratic, it does use the sign of the determinant, but the question is the determinant of what are you taking where? So the sign we're using has three pieces. One is you take the spinor norm of a certain representation that you construct of your finite group of this. It has to be a disconnected group because you're dealing with possibly disconnected situations. And the second is a hypercohomology construction having to do with squaring map on certain character modules. And the third one comes from Moy-Prasad theory. And all of these three things together has to move in order to make things work. So it's not just twisting by the sign of the determinant by any means.
Right. So can you tell me what the lemma what's the number of the lemma in that paper?
If you send me an email, yes, I don't have the exact number off the top of my head. I used to, but not anymore. But I'm happy to look it up and send it to you.
Yeah.
But to be clear, that error is in a paper of Girardin on the Weil representation.
That's correct, from 1977.
Can I go back to my first question, which now that you've got to the end seems to be, you don't get, you said that you don't get all the supercuspidals.
Right.
One reason is as you said, you're using this construction of JKU or this modified version that's now presumably correct. But so suppose that this part all worked out and the shallow part worked out and all that, what would you still be missing, or would you be able to use Jessica's result eventually, or one of these other results to say you capture everything or not?
I don't know.
Regularity, so, you mentioned the regularity.
The regularity is not a problem anymore. So that was a work of mine done earlier, but now this is not imposed. We do get all supercuspidal parameters.
Oh, so you do?
But parameters, not representations. There is a difference between the parameter being supercuspidal and the representation being supercuspidal. The parameter being supercuspidal implies that the outpacket consists entirely of supercuspidal representations. Right. Now, to match packets, to match supercuspidal representations with non-supercuspidal discrete series representations, to me at least, the way I would approach it is I would need to understand those non-supercuspidal discrete series. And our understanding of general non-supercuspidal discrete series at the moment seems to be rather limited. Of course, Lustig has work for unipotent representations. But if you go beyond that, at least I don't have sufficient understanding at the moment. So at the moment, I wouldn't know what to do.
So as a complete outsider novice, suppose you took GLN, where you don't have this endoscopy problem, and you wanted to prove the local Langlands for GLN by this, say, by Kutzko and that kind of style, which is completely explicit, which seems to be partly what JKU does. There's no proof. Has anybody ever proved the local Langlands for GLN directly like that?
I don't know that anybody has tried. Of course, first of all, you'd be missing the low primes, right? So there, I wouldn't know what to do. And I don't think these methods, at least at the moment, penetrate into that range.
Peter?
Yeah, somebody can.
Alan Moy, in his thesis in the 1980s.
Hi, Roger.
Hi. I showed that at least for the supercuspidal representations that had been constructed at that time, there was consistent with the Langlands conjecture correspondence.
Yeah. Mm-hmm.
I mean, a lot has happened since then, but for those representations at that time, Alan Moy showed that the correspondence was consistent with Langlands.
Great. This must have been a very special lecture to get Roger Howe to it. Right.
I am overjoyed.
Great to see you.
Likewise.
Can I ask another question?
Yes, please.
So the finite torus Fk, right? It is true that
please?
So I mean the K point of S, right?
I'm having trouble understand. I'm sorry.
So when you look at the K points of S,
the K points of S also over the finite field, yes.
Right. So is it true that it lies in no proper Russian parabolic?
S is not going to lie in any rational parabolic.
Right.
Yes.
Yeah, I just want to be sure. So it means that your result apply only to this kind of S. I mean, like I want to see whether your result can be applied to any other Maxwell torus of a finite group of Lie type.
Oh, which result? This one?
Yes.
So this result is for a elliptic maximal torus, and a non-singular character. But in the setting of a disconnected reductive group, in the setting of a connected reductive group, this result follows very easily from Lustig's work already. But when the group is disconnected, it becomes more complicated. But I've not even thought, of course, the question makes sense when you have a non-singular character of a torus that's not elliptic. But yeah. I've not thought of that because, you know, I didn't need it for the purposes that I had.
Thank you.
You're welcome.
So why wasn't this error discovered before? I mean, people were already computing these Hauer-Chandra characters, right?
It's I don't know. I mean, this was certainly a well-known paper, and it took, you know, such a long time, almost 50 years, you know. And I don't know. I mean, it just goes to show that such errors can go undetected for a very long time.
So, for example, you already did regular supercuspidal.
The problem of the subject. The subject involves a tremendous number of calculations, and if you don't have a side intuition of checking that various formulae are correct, nobody wants to go check every formula. So this has happened with other things too, with some sign being the opposite of what people thought, and then a whole philosophy being wrong based on that. So it's very important to have kind of checks and balances which say the formula can't be right. And it's not that surprising if somebody wrote a paper which this wasn't so important to them. But on the Weyer representation, yes, Roger, how does somebody get, yeah, I guess you can't get a sign wrong in the Weyer representation very easily.
But in particular, like, so these extra terms, why don't they come up for regular supercuspidals?
Yeah, that's very, it's the sign in the Weyer representation is definitely tricky. And so I wrote a paper titled on the character of the Weyer representation, but I only computed it up to sign. So
up to sign.
So Roger Howe asked me a question in the chat about how, if one looks at my results in SO2, how is this relates to the theta correspondence? And that's not something that I've studied. However, I'm quite interested in this, and I've discussed this a little bit with Jeff Adams, because this is something I didn't mention in my talk. There was not enough time, but this character formula here that I wrote down, this character formula can actually be stated more canonically if one considers not the torus itself, but a certain double cover of that torus. And people like Jeff Adams and David Vaughan have worked with these double covers in the real case, and they are related to the metaplectic group and the Weyer representation, at least for real groups. And I have a construction of the same kind of double cover for p-adic groups. And I've always wanted to understand how this construction relates to the Weyer representation. And so far, I'm not entirely sure. So I think in the case of SO2, this is the most approachable situation. But it's unclear at the moment, so I don't know.
Yeah, well, Jeff Adams is definitely the expert in this area. Yeah.
Yeah, so I had once a discussion with him, and we didn't immediately see the connection because it seemed that the double covers that the Weyer representation would produce do not quite agree with the double covers that are produced from this point of view. Of course, there may still be a relation that we just didn't see. And regarding Alan Moy's thesis, I have not looked at that, so I'm not, I mean, I have looked at that at some point, but I have not compared it to what I do, so I'm not sure.
Okay, but something to look at.
Yes, thank you. That's certainly something interesting to think about. Tony, what was, oh yeah, so these things do come up in the regular case, absolutely. And they've come up already in earlier work of De Backer and Spice and so forth. And the going technique was to just forget about them. So what happens in the regular case, or even in the simpler Toro cases, is that you can just absorb them into this theta here. And those error signs are quite patient. They're invariant under the full Weil group. And so if you have a regular theta and you multiply it by something that's invariant under the Weil group, the result is still regular. And you say, oh, I'm just going to reparameterize my correspondence and then everything will line up. But from that point on, there was already a feeling the correspondence is not quite right. We need to reparameterize it. But once you go beyond the regular case, all of a sudden, the properties that this theta has, the non-singularity property, is much more subtle. And there is absolutely no reason to believe that if you multiply it by these Weil invariant characters, the result will still be non-singular. And so that's where I got very worried. And because it seemed things are just crumbling down. And it took us a lot of work to be able to, first of all, find an extension of these characters. At that point, we knew, okay, they extend sufficiently, so the product of theta with them will be non-singular. We can still do this ad hoc modification, reparameterization, but philosophically, that wasn't quite satisfying. We needed to know what's really going on. And so it's a lot of extra additional work. Eventually, we're able to find this modification of the construction that not only lines up the character formulas, but in fact also restores the validity of these intertwining results, which we're now looking into for further applications.
But does that mean that this parameterization is actually different from the one in the regular supercuspidal paper, the kind of older paper?
No, it's not, because there I just absorb these into the theta so that these the two character formulas star and double star line up. And absorbing these into theta has the same effect as using the modified U construction, at least in the regular case.
Okay.
So there is a paper by Thomas who seemed to give you the explicit sign for the representation. I mean, for the character values in representation.
Teruggi Thomas, yes, I'm aware of the paper.
So that is correct. The mistake of Girardin.
I've not compared to whether Thomas's paper lines up with Girardin's paper and in what way. What we have used is the corrected version from Girardin's paper, where we took the formula from the proof rather than the formula from the statement.
I see. Thank you.
Are you able to give any examples of just an example of what's supposed to happen in these non-supercuspidal L packets?
Oh, where you have discrete series, non-supercuspidal discrete series, and supercuspidal representations?
Yeah, just like one example of what's supposed to be true.
I have not seriously looked into that. I'm aware of the constructions of Lustig. And there is also the opposite end of the spectrum, where you're looking at unipotent supercuspidal representations. And people like Opdam and Sollefeld have worked very hard on this and have pretty complete results by now. And so you can look at their papers and see what's happening there. But I don't have any serious knowledge on this subject.
I feel like the people who work very hard on these kinds of things, they always have such a general perspective that you look at the paper and you can't find like a particular example that you can get your hands on.
Yeah, you're right. The examples, well, as far as this project was concerned, the examples I like to think about was, first of all, SL2, that's my favorite. But then I also looked at some certain, when it came to studying the situation with higher multiplicities here, where did it go? So that was a really difficult example to construct. And so for this, you needed to take two ramified unitary groups that are ramified in different ways and glue them together and also ramified torus. And the example is horrific, but you know, that's another example. Or you can look at spin 9 and you can describe things there. So of course, very quickly the examples become maybe less pleasant than you might hope. And so that may be a reason why people generally avoid giving examples.
So maybe we should thank Tasho again.
Well, thank you. It was my pleasure.
Very nice talk.